So in the case of the Fourier series used to represent any arbitrary signal into, as we have discussed yesterday, weighted sum of or linear combination of harmonically related complex exponential, right? So you can write here Fourier series. Fourier series is nothing but, the representation. It is the representation of periodic signal may be the continuous or maybe the discrete, no problem. So it is the representation of the periodic signal into the using the linear combination of, you can write here, linear combination of harmonically related related complex exponential, right? Complex exponential. Or in other word, you can also write as the weighted sum of harmonically related complex exponential. Both are the same, right? Both are the same thing. So it may be this representation may be used for the, as we have discussed, continuous. This representation may be used for continuous time as well as the discrete time, right? So in the case of continuous, it is known as CTFS, very well known, CTFS, continuous time Fourier series. And in the case of discrete time, the used terminology is the DTFS, discrete time Fourier series, right? Discrete time Fourier series. So now I'm going to the detail of before going to the detail of the, about the Fourier series, you have to know about if you're interested to know about the French mathematician JBJ Fourier, right? So he's a very great personality. Why I'm saying great personality? Because he is actively involved. Wait a minute. Okay, so as you know, he is the very great personality. Why I'm saying the great personality? Because he is the actively involved. Not only he is a great mathematician, the Fourier is not a very great mathematician. As at the same time, he is actively participated in French Revolution. Okay, so it is the actively participate in the politician, right? And also he is the hardcore you can say a religious personality, right? Religious personality. So at one time he had left all the research and mathematics and all these things, and he had joined the Prest University and Prest College and teaching the religious subject, right? After some time, he has also actively participated in the, the politics, and he has very good term with the, Napoleon. Okay, so now, as you know about the Fourier, Fourier is a great mathematician. Why I am saying? Because when he proposed the, you know, actually his journey started with, one of the, topic. That topic is, heat conduction, right? So as in the year 8007, 81807, in 81807, right, he has proposed a mathematical work on the theory of heat. Okay, mathematical work. He has proposed a mathematical work on theory of heat, right? And he submitted his work. He has submitted his work, right? Uh, and the topic was on the propagation of heat in solid bodies, right? So basically, he helped to solve the partial differential equation with the help of, difference. He tried to solve the partial differential equation with the help of Fourier series, right? So the one committee has been constituted for the revision of this paper, right? The committee, it is very important. The committee was consisted of, at the time of that time, the great personality was a Lagrange, as you know, Lagrange, Laplace, right, Monge, and one other is the Lacroix, right, Lacroix. So these are the personality who the committee was constituted to review this paper on the propagation of heat in the solid bodies, right? And at that time, uh, basically Lagrange, Laplace, and Monge and Lacroix, all these mathematician have taught the Fourier. Fourier was the student of this personality, right? And when Fourier proposed this techniques, Fourier series in the for the solving the problem of propagation of heat in solid bodies, right? So at that time, his work was, all these committee are very unhappy for with this work, right? Unhappy with this work, and at that time, the committee has rejected his work, right? The committee has rejected his work, and after approximately 20 years and after 10 to 20 years, the theory was accepted, right? The theory was accepted. So this is the short story of, uh, about the Fourier. So if you want to know more about the Fourier, you can log in with the Google and, search about that. So before going to the detail of the Fourier series, okay, we have to know about the condition for existence of the Fourier series, right? So the condition for existence of Fourier series expansion, right? So the condition is known as Dirichlet condition. It is very important condition. Anybody can tell me what is the Dirichlet condition?
चार कंडीशंस बताई थी सर इसने
हाँ, कौन कौन से
मेनली तो
बताओ जरा, याद
सर
है तो।
एक तो फंक्शन सिंगल वैल्यूड होना चाहिए
हाँ,
और मैक्सिमा मिनिमा फाइनाइट होनी चाहिए
वेरी गुड, वेरी
एक
गुड,
पर्टिकुलर टाइम इंटरवल में
वेरी गुड, यस,
और एब्सोल्युटली इंटीग्रेबल होना चाहिए function।
वेरी गुड। सो
चौथा सर याद नहीं
कोई बात, तीन ही कंडीशन है, देयर आर थ्री कंडीशन ओनली। फर्स्ट कंडीशन is the signal should have finite number of maxima finite number of maxima and minima over its time period, right? So what it means? So signal should have the finite number of maxima and minima over the time period. ये होना चाहिए. Let's say I'm giving one example, right? So let's say this is the one example I have taken. Let's say this is the x1t. The total time period of this signal is, let's say, t naught, right? The amplitude of the signal is nothing but the a naught, let's say, and this side is the minus a naught, right? So the number of maxima minima of this period is fixed, right? So x1t, the Fourier series expansion is possible in this case. However, let's say I am taking the second example, x2t. Let's say we have a signal like this one. Okay, so let's say this is the signal x2t. Okay, and similar way there is also signal here, right, based on this. Like this one, right? So this is the x2t, right? So let's say this is the signal with some amplitude a whatever, right? And this is the 0, this is the t naught, let's say, and this is the 2t naught, like that, right? 2t naught. But you know, you are not able to find out the finite number of maxima and minima in this case, and therefore the Fourier series expansion is not possible in this case. So where there is not possible to find out the number of maxima and minima, where you are not able to use the Fourier series expansion. Second condition of the Dirichlet is, as Pramod said, signal should have finite number of discontinuities over its time period. Means, let's say we have one example, the square wave pulse. So here x1t, there is a discontinuity here for up to, you can say here, up to this point, right? This is the discontinuity. Hai? There is a discontinuity. So we have, if there is a finite number of periodic signal is there. So let's say this is the t naught. So in the one period, you can calculate the finite number of discontinuities. However, in this case, so x1t, you can comment on the x1t, the Fourier series expansion. Is possible. Number of discontinuities is equals to 2 for one period, right? However, let's say we have another signal. So let's say this is the signal, right? So x2t, let's say this is the x2t. So x2t is, you are not able to find out the number of discontinuities. However, the signal is continuous. Discontinuous in this picture. So you can say that Fourier series expansion is not possible. right? So now you tell me, what about the tan t? Is Fourier series is possible? Expansion tan t. What is your comment? What do you comment? Fourier series tan t for tan t. Okay, third. First to see the third, then we will start. You are signal should be absolutely integrable. Absolutely integrable over its time period. Over its time period means over a one time period you are able to calculate the integration of that function xt dt, right? So the integration of this function is less than, we are able to find out the finite value, right? So it is the these are the three criteria must be passed for expansion of the Fourier series, right? So now just to comment on the tan t, is the Fourier series possible? Is the Fourier series expansion is possible? Is Fourier series expansion possible? Yes, students, please tell me. Hello. हाँ भाई बताओ, टोपो, अनिशा टोपो,
Yes, sir. Sir,
पॉसिबल?
Fourier series expansion.
हाँ.
So ये 2 पे infinity को include करता है तो
For the
मे बी
tan t, for the tan t, my question is, for the tan t, is the Fourier series expansion possible or not? Based on these three criteria. बोलो टोपो.
सर नहीं होना चाहिए।
नहीं होना चाहिए. चंदन.
यस सर।
बताओ
सर होना नहीं चाहिए
क्यों नहीं होना चाहिए?
सर, क्योंकि
क्यों?
ये सर एरिया अंडर द कर्व इनफाइनाइट हो जाएगा ना सर, tan t
वेरी
के
गुड,
लिए।
वेरी गुड, वेरी गुड. सो tan t का जो एक्सपेंशन है वो इसलिए नहीं होगा क्योंकि आपका माइनस इनफाइनाइट से इनफाइनाइट तक एग्जिस्ट नहीं करता, और दूसरी चीज इंटीग्रेबल नहीं है, राइट? वेरी गुड, राइट. So these are the things, right? Now I'm coming to the types of Fourier series expansion. So as you have seen, first line was by ki Fourier series is a representation of the linear combination of harmonically related complex exponential, right? So there are two techniques used for the expanding the Fourier series. So first type was type of Fourier series expansion. So first is the trigonometrical Fourier series expansion. So in this case, the Fourier series expansion is written in this form: xt is equals to a naught plus summation of n is equals to n is equals to plus 1 to infinite an cos n omega naught t plus bn sin n omega naught t, right? Where a naught is calculated with the help of this equation 1 by t naught integral over one period t naught xt dt, right? So it represents the dc value or average value. It represents average or dc value of signal, right? However, an is given with the help of the formula 2 by t naught xt cos n omega naught t dt, right? So it is nothing but, the even function with respect to n. However, Bn is nothing but the 2 by t naught, the integration over one period xt into sine n omega naught t, right, dt. So it is the minus Bn. So it is the odd function with respect to n, right? We will discuss more after some times how it will be evaluated, how it will be found. So one method is of representation of the Fourier series like this one. Okay. So in the signal system, we are not using this type of, expression. We are generally using the expression, second expression we are generally using, that is the harmonically related, linear combination of harmonically related complex exponential, right? So second method is the exponential Fourier series expansion. And in this case, it is represented like this: Cn is equals to xt is equals to summation of n is equals to minus infinite to infinite Cn e to the power jn omega naught t. Right. This is the Fourier series representation. So as we have said, first of all, see here. Cn, what is Cn? Cn is the complex exponential Fourier series coefficient, right? Where it is given by the formula 1 by t naught, integration 1 over 1 period, xt to the power minus jn omega naught t dt, right? So we'll discuss later in the detail of this one after some time, right? So before going to the detail of this, you have to understand what is the meaning of Fourier series. So when I said the term linear combination of harmonically related complex exponential. So linear combination means which follows the simply superposition theorem, right? In the superposition theorem means it follows what? Tell me. Homogeneity and what? Tell me. Homogeneity and yes,
Additivity.
Very good. Additivity. And harmonically related means, what do you mean by harmonically related? Harmonically related, as we have said earlier.
Multiple frequencies.
Yes, multiple frequency. Very good. Multiple frequency. And the complex exponential is nothing but the e to the power j n omega naught t, right? E to the power j omega naught t. So if we say this is let's say this is a circle, so it is the e to the power j n omega naught t, and if I represent this side, then it will becomes e to the minus j omega t. The time period of this is a 2 pi. Okay, the time period of this signal is 2 pi. Okay, so we can say here that xt is, let's say I'm writing k equals to minus infinite to infinite a k e to the power j k omega naught t, right? So it may be written as a k equals to minus infinite to infinite a k e to the power j k. The value of omega naught t is nothing but the 2 pi by t naught t. Okay, so this represent what is the linear combination, right? This summation represent the linear combination, right? This is the linear combination. What is this? This is what is the k. If you put the k equals to 1 and k is equals to -1. So what it represent? It represent the first harmonic. It represent the first harmonic. If you represent the k is equals to 2 and k is equals to -2, then it represents the second harmonic, and so on. And when you say about the k is equals to n and k is equals to -n, then it becomes the nth harmonic components, right? Nth harmonic components. And what happened when the value becomes k equal to 0? So the value when k equal to 0 becomes, then it will become the constant, right? This is a constant, and it will provide the DC value or the average value or the DC value, right? So it is the harmonically related picture. It is the harmonics, and so linear combination of harmonically related, right? And when you say the e to the power j k omega naught t, when you say e to the power j omega naught t, so it is nothing but the this is the complex exponential, right? Complex exponential, e to the power j omega t. So it is nothing but the complex exponential. Complex in the polar form, it can be written as a what? Please say cos omega t plus j sin omega t. Am I right? Yes or no? Cos omega t plus j sin omega t. So yesterday we have taken up one problem that was, I think, not clear to all of you. Today once again I'm going to discuss that problem. Then we will starting with the Fourier series. In order to understand the above problem of the harmonically related complex exponential linear combination, please see this example. This example is given as a, let's say, given a continuous time periodic signal xt is equals to summation of k is equals to -3 to 3 a k e to the power j k 2 pi t with fundamental frequency 2 pi, right? Also where coefficient is given, coefficient r a naught is given as a 1, a1 equal to a minus 1 is given as a 1 by 4, a2 is equals to a minus 2 is given as a 1 by 2. Very important example, please see, a3 a minus 3 is equals to 1 by 3. From this example you are able to understand the relation of harmonically related complex exponential, right? So the problem is so graphically how the xt is built up from its harmonic components, right? So please see the solution. xt is equals to, xt is given as a what? Summation of k is equals to -3 to 3 a k e to the power j k 2 pi t. Screen is visible, na? Yes or no? Any delay today?
No, sir.
Okay.
No, sir.
Yes, sir.
Okay. So ध्यान से देखना, xt is equals to k is equals to -3 to 3 a k e to the power j k 2 pi t. So how it be written? It may be written as a of -3 e to the power j, it may be written as a e to the power minus j, when you put the k is equals to 3, 2 pi t, right? Then a of -2 e to the power minus j 2 of 2 pi t plus a of minus 1 e to the power minus j, right? 1 into 2 pi of t, okay? Plus a naught e to the power minus j 0 2 pi of t, right? Plus a1 e to the power j 2 pi of t plus a2 e to the power j 2 into bracket में 2 pi of t plus a3 e to the power j 3 2 pi of t, right? What is the value of a3, a minus 2, a minus 1? You can put here, okay? So with the help of the above expression, the value of a3, a minus 3, a minus 2, a minus 1, a naught, a1, a2, a3, just to put. So value of a3 is 1 by 3, okay, e to the power minus j 6 pi t plus value of a minus 2 is 1 by 2 e to the power j 4 pi t, sorry, minus में, right? Then 1 by 4 e to the power minus j 2 pi t plus a naught. The value of a naught is 1. When you put this 1, this is a 0, so it becomes 1. Plus a, what is the value of a1? A1 is 1 by 4 e to the power j 2 pi t, right? What is the value of a2? A2 is 1 by 2, so you can write here 1 by 2 e to the power j 4 pi t plus 1 by 3 e to the power j 6 pi t, right? Any problem? Any problem? Guys, अरे बोलो भाई, हाँ या ना, कुछ तो बोलो. Okay, so 1 by 3, when you take the common, e to the power minus j 6 pi t plus e to the power j 6 pi t. Similarly, you can take as a 1 by 2, 1 by ये हो गया 6 वाला, 4 वाला ले लो, 1 by 2 e to the power minus j 4 pi t plus e to the power j 4 pi t, right? Plus 1 by 3 हो गया, 1 by 2, okay, 1 by 4 e to the power minus j 2 pi t plus e to the power j 2 pi t, right? And 1, okay? So it becomes value 1, okay, plus इसमें 2 से डिवाइड करके 2 से मल्टीप्लाई कर दो, 2 से डिवाइड करके 2 से मल्टीप्लाई, 2 से डिवाइड करके 2 से मल्टीप्लाई, right? So it becomes what? It becomes 1 by 2 और ये बन गया cos 2 pi t, right? Cos 2 pi t, right? This is the cos 2 pi t. This one is cos 4 pi t, 2 cancel, or it becomes cos 4 pi t, and it becomes 2 by 3 cos 6 pi t, right? 6 pi t, okay? So this is the xt, so if I'm right, this is the x naught t, this one is x1 t, this was the x2 t, and this is the x3 t. If this is the x3 t, then overall x naught t, overall xt can be written as a x naught t plus x1 t plus x2 t plus x3 t, right? This is the combination. This is the linear combination of the harmonically related, okay, complex exponential, right? So complex exponential से आपने क्या लिखा? Complex exponential से आप लोग harmonically related हम लोग बना लिए. Yes or no? Yes or no? Any doubt up to this point? Please ask.
No, sir.
Okay, so this is the construction of signal, right, from its harmonic components, right? Now see so it's graphically. The problem is we have to show this problem with the help of graphical representation, right? So see here, x naught t is 1, x1 t is 1 by 2 cos 2 pi t, x2t is cos 4 pi t and x3t is 2 by 3 cos 6 pi t, right? So based on this, when you draw the x naught t, and your x naught t is nothing but the 1, right? This is the x naught t. X naught t is equals to 1, right? Now when you say about the x1t, this is the 1 by 2 cos 2 pi t. So it is nothing but, you know, the magnitude is 1 by 2 and the magnitude is 1 by 2 and this is the cos function. So you can simply draw like this one. Yes or no? Am I right? So this is the simply cos function, right? And when you add x naught t plus x1t, when you add this one x naught t, sorry, x naught t, when you add x naught t plus x1t, so how it will represent? It may be represented like this one. It may be represented like this one. Right? This may be represented like this one. The idea is this one, right? Now, when you draw the x2t, what is x2t? x2t is nothing but the cos 4 pi t. Cos 4 pi t. What does it mean? So it is the second harmonic. Yes or no? Yes or no? Second harmonic. तो second harmonic क्या हो जाएगा? इतने पीरियड में ये जो वन पीरियड है आपका फ्रॉम दिस टू दिस, राइट? इतने में कितना रिपीट होगा? 2 बार, राइट? तो उस तरह से आप बना ले. सो आप इसको कुछ इस तरीके से कॉम्प्लेक्स करके सिग्नल को, है ना, सिग्नल को कुछ इस तरीके से बना ले, राइट? कॉम्प्लेक्स करके आपको, सॉरी, in similar way you can draw like this one. Is it any problem? Yes, please ask. T, that is the cos 4 pi t. ठीक है? तो इस टाइम में कितना हो जाएगा? आपको पूरे आप 2 बार रिपीट कर लीजिए सिग्नल को. When you add this signal, तो आपको ऐड करना है किसके साथ? x naught t plus x1t plus x2t, right? आपको ये ऐड करना है this plus this, right? When you add, then you will got like this one. Right? You are already studied the DAT, na? Data acquisition theory. Yes or no?
इसी सब में है सर.
डाटा DAT चल रहा है ना आप लोग का?
यस सर.
तो DAT में आप लोगों ने पढ़ा होगा फ्रीक्वेंसी, आपने वो आप AM FM पढ़ा ना? फ्रीक्वेंसी मॉड्यूलेशन, AM मॉड्यूलेशन और फेज मॉड्यूलेशन. यस और नो?
यस सर.
तो मॉड्यूलेशन में इस तरह का पिक्चर आया होगा. यस और नो? आपने ऐड करना सीखा था ना? आप वहां पे सीखा है कि नहीं सीखा है? तो कुछ इस तरीके का सिग्नल बन के आता है. क्लियर है? और व्हेन वी आर टेकिंग द 6 pi t लेंगे और कॉम्प्लेक्स हो जाएगा, है ना? x3t is 2 by 3, the magnitude is only changing. However, this is the third harmonic, right? तो थर्ड हार्मोनिक में क्या होगा? 3 बार रिपीट हो जाएगा, राइट? इस सिग्नल में आप क्या करेंगे? 3 बार रिपीट कर देंगे और स्पेस कम हो जाएगा और सिग्नल कुछ इस तरीके का, है ना, कुछ इस तरीके का बन जाएगा, राइट? है ना, राइट? कुछ इस तरीके का सिग्नल आपका, कुछ इस तरीके का सिग्नल बन के आएगा. ठीक है? और जब व्हेन यू ऐड दिस वन अगेन विद दिस, क्या आ जाएगा? उस सिग्नल आपका कुछ इस तरीके से राइट, कुछ इस तरीके सिग्नल बन के आ जाएगा, राइट. सो दिस इज द फाइनल सिग्नल x0 t plus x1 t plus x2 t plus x3 t, right. So this harmonic is clearly realized here. However, the first is the looking here, right. First is this one, and due to the second, third, fourth harmonic, it will come like this one, right. Okay, is it any problem? Please ask. No? If no, then I will proceed further. Is it okay?
Yes, sir.
Right. So now come to the determination of okay. Next is the derivation of okay. Before this, wait for a minute. I want to discuss one more thing, then we'll go there. Now see, in the above example, you have seen a minus 1 is equals to a1, a minus 2 is equals to a2, however a minus 3 is equals to a3, right. These are the things we have realized. Okay, so if the signal xt is real, right, if the signal xt is real, then you know x star t, the conjugate, is nothing but the xt. ये होगा, where x star t is the complex conjugate of xt, right. Now since x star t, since the signal is real and therefore the complex conjugate is the same, right. So if this is the, if xt is equals to x star t, then it means xt is equals to nothing but the summation of k is equals to minus infinite to infinite a k star e to the power j minus j k omega naught t, right. And as we know that x, when you replacing k by minus k in the above summation, right. So xt becomes k equals to minus infinite to infinite, or you can again minus, this becomes infinite, this becomes minus infinite, right, the summation, and again becomes, it becomes my k equals to minus infinite to infinite, and it becomes a to the power a minus k star e to the power j k omega naught t, right. Right. However, we know that, as we know that xt is equals to summation of k is equals to minus infinite to infinite a k e to the power j k omega naught t, ये हमारा होता है already, right. So from this expression we can write here ak is nothing but the a minus k star, or ak star is nothing but the a of minus k, both all are the same. Like that, a minus 1 is nothing but the a1, a minus 2 is nothing but the a2, and all like that, right. So based on this, is there any problem? Is it clear now? Okay, so now come to the next point, where derivation of alternative form, alternate second form. That is the first form we have already discussed in the form of, you know, trigonometrical exponential. How this will may be written? Please see, derivation of alternative form of fs, Fourier series. So as we have seen, xt is equals to nothing but the summation of k is equals to minus infinite to infinite ak e to the power j k omega naught t, right. We already have seen. So when you expand this term, like a naught plus k equals to minus infinite to infinite, right? K equals to minus infinite to infinite. A k e to the power j k omega naught t plus a of minus k e to the power minus j k omega naught t, right? The positive term and the negative term we have seen, we have written here, right? Like this one. Let's say we have writing the 0 here, negative side this one, positive side this one. This is the negative side. The negative side is the positive side, and this is the 0 term, right? We have written here. And as we know that a k is equals to nothing but the a k star. Okay, so based on this we can write here a naught plus summation of, sorry, this is the not k is equals to, it becomes k is equals to 1 to infinite, right? Because we have already written this one. Okay, we have already written this one a naught, so 0 term is already, 0 will not include here. Okay, and the k is equals to from minus infinity to 1 and 1 to infinity is here, right? Is it any problem? Please ask. Minus infinity to minus 1 and then 1 to infinity, because 0 is already we have included, right? So based on this we can write here ak e to the power j k omega naught t plus ak star e to the power minus j k omega naught t, it is minus j k omega naught t, right? Okay, so it is nothing but the real part. We have already discussed, this is the real part. So xt is equals to a naught plus, this is the one real part, this is the second real part. When we add, it becomes k is equals to 1 to infinite 2 real part, right? Of what? ak e to the power j k omega naught t. I think it is clear. Okay. Okay. So if let's say ak, if the coefficient, if the Fourier series coefficient ak is expressed, let's say in polar form. In polar form, what is the polar form? Polar form is nothing but the alpha k e to the power j theta k. Yes or no? Polar form आप समझते हैं ना, cos j omega t plus sin j omega t. Yes or no? So it may be written as a cos theta k plus j sin theta k. This is the scene, and the coefficient, the constant is this one. Okay, so xt becomes a naught plus, अरे पूछ लो अगर कोई प्रॉब्लम है तो just you can ask. Okay, summation of k is equals to 1 to infinity 2 real part. The value of ak is alpha k e to the power j theta k, and this one is the e to the power j k omega naught t. Okay, so it becomes a naught plus summation of k is equals to 1 to infinite k is equals to 1 to infinite 2 real part, right? Alpha k e to the power j k omega naught t plus theta k, right? And when we represent this one in the term of polar form, summation of k is equals to 1 to infinite 2 real part of what is alpha k cos k omega naught t plus j sin k omega naught t, right? So this is the term in this term also we can write. And when we solve this final term xt, so it becomes 2 summation of k is equals to 1 to infinite alpha k, and when the real part is represented, then it becomes final equation is cos k omega naught t plus theta k, right? So this is the final term. We can represent like this one. We can represent also like this one, right? In the term of cosine, sine, and a naught. Okay, this is a DC value. This is the cosine value, this is the sine value, right? So with the help of this one, with the help of this, we can write this equation. Okay. So next part of discussion is only remain the determination of कोफिशिएंट. अब ये एक एक फाइंड कैसे करते हैं, जो हमने एक्सप्रेशन देखा है फर्स्ट हम लोग जो स्टार्ट किए थे लेक्चर अपना, व्हेन वी स्टार्टेड टू द लेक्चर, यू कैन सी हियर, yes, this one, okay, this one AK, where we have written here CN or maybe AK, both are the same. So how the AK is determined, okay? So this is the problem. Now we have to going to solve or study this point, okay? So determination of Fourier series coefficient, determination of Fourier series coefficient, right, of continuous time Fourier series signal, continuous time Fourier series periodic signal, right? So we'll discuss these things at 11:30 today, right? 11:30 today lecture. Is it any problem? Yes, students. I am taking the attendance right now. I am taking the attendance. So today is 18 November. Baba is absent. Baba?
No, sir. Present.
Present.
Present, sir.
First of all, I am stopping the